Welcome to video 2 of our IB Biology Topic 5, Evolution and Biodiversity, looking at 5.1, so that's evidence of evolution. The second video, so it's video 2 of this section, 5.1, because there's quite a few concepts in this section that, although we revise them again or go into them in much more depth in later sections, it is quite a big topic to section to cover, this evidence of evolution. So in our last video we looked at that whole concept of evolution. We looked at natural selection, variation. We'll go into more depth of variation coming up. We looked at the fossil record and how that gives us evidence for evolution, and now we're going to move on to kind of domestic selective breeding in domestic animals, and then looking at some of the structures in organisms to see how they support the theory of evolution. So looking first of all at selective breeding and artificial selection. So this in our society today is quite popular as such, in terms of agriculture, with livestock, so cattle, sheep, horses, pigs. Selective breeding is really important to get the most effective animal for what you're breeding it for. With even household animals such as our dogs that we've got here, selective breeding to get the desirable traits is extremely important. Cats as well, rabbits, guinea pigs, hamsters, goldfish. So if we look at this from an evolution point of view, in recent history our science of breeding has managed to give us a good record of the recent changes in heritable characteristics, and then we can relate this to how species change over time. So evidence from selective breeding and that artificial selection. So artificial selection is where humans select the desirable traits in domesticated animals. So for example, when a farmer notices a trait that an individual would be allowed to mate, so this trait is selected for. So for example, if you're looking at dairy cattle, if you've got a cow who is a good milker, gives a good amount of milk, then she is a good animal to be bred with, because then any offspring, female cattle will be good, hopefully will be good milkers as well. Now when an individual displays a negative trait, it will not be allowed to mate, and therefore we select against that trait. So with sheep, you might have an animal that has a low wool ratio, and in that situation, if you are a farmer and part of your income is from wool production, you want sheep who produce a nice amount of good quality wool. So you wouldn't breed one that's a poor wool producer, because then you get more sheep that produce poor qualities or poor amounts of wool. It's clear that domestic breeds of animals have not always existed in their current forms. So if we have a look at this chart here, we can see how the horse has evolved over time. And the horse as we know it now in the top left hand side there is very different to, if you go down to the bottom, to its history, ancestral forms. Sorry, couldn't think of the word. So evidence from physiological structures. So we are looking, remember, for this evidence of evolution. We've looked at evidence from the fossil record. We've looked at artificial selection and how that gives us some evidence of evolution. We can see how those changes can occur. Now we're going to look at some physiological structures. Okay, now we've got some terminology here. Homologous structures are similar in structure but not in function, found in seemingly dissimilar species. So similar in structure but not in function. So here we've got our pentadactyl limb. Okay, so in humans it's the arm. Pentadactyl, 5 digits. Okay, so we've got 5 fingers. Alrighty, now if we look at the cat, very similar to the human, but the cat leg is used for a very different function than the human arm. Okay, the bat, look at the bat wing, very similar in structure to that human arm. It's got those 5 digits, okay, but a very different use of them. That's the same thing, just in a different kind of view. Okay, some more homologous structures. Okay, so we're looking at the beaks of these finches and we'll be looking much further into this. Homologous structures, though, provide evidence that these species has evolved from the same origin. As a result, they now perform different functions. So evolved from the same origin, but have evolved to perform different functions. Okay, now this kind of evolution is what we call adaptive radiation, a type of divergent evolution. So you think divergent, going on different paths, where one ancestor gives rise to many different species. And here we've got the finches, and their beaks now have different roles in terms of what they do with those beaks. Now, our pentadactyl limbs, okay, we've got 5-digit limbs, as I said, of vertebrates. These are our homologous structures, indicating a close relationship and to a common ancestor, but their functions demonstrate adaptive radiation. Now, we look more at adaptive radiation in a later unit. Okay, so we've looked at homologous structures. Now we also have analogous structures, and these are features that have the same function but not the same basic structure. Okay, so let's have a think about this. If we look at homologous mammals, okay, so we've got the cat leg and the whale flipper. Okay, so they're homologous. They're both pentadactyl. They've got the 5 digits. They are so similar in structure but very different in function. Okay, then we've got our homologous insects. So they've got the praying mantis leg and the water boatman flipper. Same structure, very different use. Okay, however, analogous means they have the same function but they're a different structure. Okay, so the cat leg and the praying mantis leg, very similar in what they do, but different structures. Okay, and the whale flipper and the water boatman flipper leg, very different structures, but the same function. All right, now we move on to the concept of speciation. Populations of species can gradually diverge into separate species by evolution. So this is what we was just talking about, where we have that common ancestor but then different species. And to explain this, we've got potato head. Now, with speciation, the formation of a new species is developed in the course of evolution. So with potato head, we started off with one potato head, and then over the course of evolution we've had more potato heads. So looking further at speciation, the processes involved for speciation to occur. We need a parent population to be divided, okay? So it could be divided geographically, all right? There's no gene flow that occurs between the two populations. Mutations can arise then in each population. Different selection pressures occur in each population due to different environments. Genetic changes are then passed on to offspring and accumulate. And even if the separating barrier is then removed, the two species can no longer mate to produce fertile offspring. And we call this reproductive isolation. Okay, so you have your initial original population, you have that geographic barrier, we're then in that reproductive isolation, and then speciation occurs. So we have two separate species in the end there. Okay, so in this infographic here, we've got our populations tend to produce more offspring than the environment can support. So we have that struggle for survival. We'll look at this in a later video, okay? But these things can affect the species in different environments. Alrighty, now let's have a look at this concept of variation. Okay, now where does variation come from? And you can see here that variation is that difference between members of a species, okay? And this is quite often on a cellular level, okay? All right, so continuous variation and the concept of gradual divergence. So with Mr. Potato Head here, first of all, let's have a think about who the ancestral species is. And that's Potato Head here. The others have all evolved from him. Now, divergence is on the map as such, we call a speciation event. Okay, so each divergent there is our speciation event. This is just some terminology that you need to just bear in mind. All right, moving on to application. A comparison of the pentadactyl limb of mammals, amphibians, birds and reptiles with different methods of locomotion. So we've already looked at this pentadactyl limb. Okay, and one of your applications is to be able to discuss those homologous structures. All right, so here we've got our pentadactyl limb in our different mammals. And you need to be able to discuss that in terms of that structure and its use. Our next application is the development of melanistic insects in polluted areas. And to look at this, we are going to look at continuous variation across the geographic range of related populations that match the concept of gradual divergence. Okay, so we're going to look at some moths, the peppered moth. And the peppered moths are found in the UK. Okay, it's a species of moths that have natural variation of two distinct colours, so they can be light and they can be dark. Okay, and you can see a light and a dark moth in the diagram there. They have a natural distribution that appears to favour a specific colouring. Our moths here again. Now, lichen is a light-coloured organism that grows on trees in a forest in Britain, in most forests in Britain. And now in the same forests where our peppered moths can be found. The light-coloured moth were a selective advantage. They camouflage into the lichen. So if we look into the diagram here, the diagram at the top is showing us some lichen. And if we look at the bottom here, we've got the light-coloured moth on the lichen. It's camouflaged. It hides from those bird predators. It can't be seen. Then what happened? The Industrial Revolution occurred. pollution covered the trees and made them dark. So what happened to our peppered moth populations? I'm going back to that because I want to tell you. The light-coloured moth began to be eaten more because the birds could now see the light-coloured moth on the dark tree, and the dark moths, then their populations increased because suddenly they could be camouflaged more. Now the diagram here shows the proportion of light and dark coloured moths, and you can see that around the industrial areas of the Midlands and London area here, there's lots of dark moths because that's where all the industrial smoke and pollution would have covered the trees. In the areas that are less industrial and have the prevailing wind coming in from the Atlantic Ocean, there's more light moths, okay? So the wind, the pollution doesn't travel that way, okay? The wind blows the pollution from the Midlands over these areas. So these are cleaner areas down in Cornwall, up in Wales there, up in the Highlands of Scotland, and you still find the light moths because the lichens are still there, okay? Or the lichens have not been covered by ash, which actually kills the lichens, but that's another story. And here we are, we've finished this section of our unit. We'll look at more of this in class. Take it easy and remember to subscribe to my YouTube channel, The ABCs of STEM.